Now we've been looking at titration curves, so let's take a look at the titration curve of this buffer system. So we have pH versus the volume of base. What would what does our titration curve look like for the CO2 baking soda system? So we can show, we'll just show with one endpoint. Okay, so at the halfway point here, that pH is going to equal okay, so at the halfway point, the pH equals 6.1. Yeah, 6.1. Okay, remember, at the halfway point, the pH equals pKa. So note that at pH 7.4, we're actually right at the edge of the buffer region. Okay. Which means that at pH 7.4, are we going to have more acid present or more base present? We're going to have more base present. Okay, so did you guys confirm that the CO2 aqueous is 1.2 times 10 minus 3?
Yeah.
Okay, good. Okay, so let's go on to the next slide here. Okay, so let's say that acid is added to the blood. So calculate the pH of blood under conditions such that the increased CO2 aqueous cannot be released as CO2 gas. In other words, we're assuming that the blood buffer is a closed system. Okay, so here's the hint. You want to do a stoichiometry calculus, then use the Henderson-Hasselbalch equation. So how are you going to figure out the new pH of blood when H plus is added? Now know what's happening. Here's our equation here. If we add H plus, in which direction does this reaction shift? Shifts toward the reactant side. Okay, so again, the pH is 7.4, we add H plus, the reaction is going to shift toward the reactant side based on those equilibrium principles we looked at earlier this semester. Okay, so again, you want to do a stoichiometry calculation first, and then use the Henderson-Hasselbalch equation again to figure out what the new pH is going to be. Okay, so I'll let you work on that for a minute. Okay, so remember, here's what we've been doing. This is our stoichiometry calculation. So what we want to do for question C is to fill in the blanks here. What's the initial amount of CO2? Yeah, so this is that number you calculated in that previous question. This is going to be 1.2 times 10 to the minus 3. What's the initial H plus concentration? Now what's the pH of usually blood? 7.4. So this is going to be the initial H plus. This is pH equals 7.4. What's the initial concentration of HCO3 minus? Yeah, so from the previous question it was, this was supposed to be 0.024 molar. Okay, so this is going to be 0.024 molar. Okay, so what we did in the past is we were saying that, this was X, and then this is going to be X, and this is going to be X. Well, we know how much H plus we're adding. Okay, so the amount of H plus we're adding is equal to, this is 0.01. So if we're adding 0.01 molar H plus, how much of the other reactants react and how much product is produced? And then we can figure how much is left at equilibrium. Okay, so if 0.01 molar H plus is added, how much HCO3 minus do we want to put in here? Yes, this also needs 0.01. How much CO2? At 0.01. Now, this is an equilibrium reaction, which means it can go in either the forward direction or the reverse direction. Now, we said that when H plus is added, that's going to shift the reaction toward the reactant side, which means if that's the case, our reactants going to be CO2 and H2O, or our reaction going to be H plus and HCO3 minus. Yeah, because you're saying that again, that if we add H plus, the reaction shifts toward the reactant side. Which means that, because see, what we're trying to do is, should we add 0.01 to the initial amount of H plus and add 0.01 to the initial amount of HCO3 minus, or should we subtract? That's what we're trying to figure out. Subtract. And then for the CO2, should we add 0.01 to the initial amount or subtract 0.01? Okay, so again, we said that you add H plus, the reaction is shift toward the reactant side. So the shift toward the reactant side is H plus and HCO3 minus. Are these reacting, which means we subtract these, or are these being produced, which means we add these? Okay, so what do we do? Okay, so who says that we need to subtract 0.01 from the initial amounts? Who says we need to add 0.01 from the initial amounts? Okay, so again, if we add 0.01 H plus, that's going to shift the reaction toward the toward the reactant side, which means if that's happening, is CO2 and H2O going to be produced, or are we going to have less of this present?
Produced.
And that means this should be, this should be produced, which means that we should subtract this amount and add 0.01 to the CO2. Okay? Okay, so this is the confusing part about these equilibrium or reversible reactions. Just because we write the reactants on the left side, products on the right side, doesn't mean that they're actually reactants and products. They can be either reactants or products. Because reaction goes in both ways. Okay, so we do that. We have 0.024 minus 0.01. So at equilibrium, this is going to be equal to 0.014. And then for this one, note that we're adding 0.01 plus 1.2 times 10 minus 3. Let me write it this way. We have 0.0012. So if we add these two numbers together, we're going to have an equilibrium 0.0112. Now we want to calculate what the pH is, but so let's just plug it into our Henderson-Hasselbalch equation. So we have pH equals 6.1, which is the pKa plus the log HCO3 minus. So our new HCO3 minus concentration is 0.014, and our new CO2 concentration is 0.0112. So when we do this calculation, our pH is going to equal okay, so let's round that to 6.2. Okay, so somehow acid is added, H plus. That's going to produce more CO2, and that's going to lower the pH to 6.2. So is this a good thing for our blood and our cells? Okay, note that in the previous slide it said that, let's see, what do we say? If the pH goes below 6.8 or goes above 8.0, the cells can't function properly and death may result. So no, that's not a good thing. If that much H plus is added to our blood. Now this assumes that the blood buffer system is a closed system. Now in part D it says, same thing, 0.01 molar H plus is added to the blood. Calculate the pH of blood under conditions such that the increased CO2 can be released as CO2. In other words, assume that the blood buffer is an open system. In other words, any excess CO2 can be exhaled through our lungs to the air. Okay, so what we're changing in this case is, note that the HCO3 minus, we subtract 0.01, so it's going to be 0.014, but in an open system, note that the amount of CO2, what happens here in an open system? If we can exhale the excess CO2. So again, this represents a closed system, which means that this amount of CO2 was added, but in an open system, the excess CO2, which is this amount here, is exhaled, which means that at equilibrium in an open system, the CO2 is going to be equal to the initial amount, 0.0012. So let's do another calculation. And in this case here, we'll say that okay, so we have pH. This is our open system. Okay, so the excess CO2 is exhaled.